So that takes us to page 2, part 2 of our guided notes on lines. And the phrase we want to keep in mind here is that a line is a line because it has a particular characteristic. And that characteristic is that it has a constant rate of change. So it's the fact that it has this constant rate of change that makes it into a line. In fact, I've put a little example here. I'm going to draw a line. So there's a set of axes. And if I draw a line, what we notice is that between any 2 points on that line, that rate of change is the same. The ratio of the change in the y divided by the change in the x is the same thing. I get what we call similar triangles. No matter which 2 points I look at, if I divide those out, I'd get the same number. That's a constant rate of change. As opposed to, if I drew something that's not a line, something that looks maybe like this, if I pick 2 points on that not a line, like from here to here, there's a rate of change. But from here to here, that's not the same rate of change as it was in the first interval. And if I went, let's say, from that first interval from here to here, we have a different rate of change. So it's that constant rate of change that's what makes a line a line. And that rate of change is so important in mathematics. We gave it a name. We gave it a lot of different names. It even has its own variable, its own formula. That rate of change of that line is called the slope. And we have lots of different ways that we refer to the slope. We call it the slope. Whoops. The letter we use for slope for some reason is M. Some people believe that maybe comes from the French word, which means to climb, which is montre, I believe, montre. But no one really knows. We use M for slope. That slope, again, is the rate of change. We refer to it as the rise, the up and down ratio, the difference in the up and down divided by the run. The rise is the up and down, the run is the left-right. That rise to run ratio, the ratio of the rise to the run. We call it the change in y. The change in the y divided by the change in the x. A lot of times when we write slope, we write it as a fraction, as an improper fraction. We don't write it as a mixed number, we write it as an improper fraction. I use that phrase change in. We have a symbol in science and math and economics and all different kinds of places that represents change. And that symbol is a little triangle. It's the Greek letter delta. So sometimes you'll see delta y over delta x. And anytime you see delta, that means a change in. Okay? So slope, we call it M, we call it the rate of change, we call it the rise over the run, we call it the change in y over the change in the x, we call it delta y over delta x. All of those different things mean slope. We do have a formula for slope. There's a technical formula for slope. And the formula for slope, when we created it, or I shouldn't say we, I was not there, but when they created it, they used 2 generic points. So we're going to call them x sub 1 and x sub 1, y sub 1, and x2, x sub 2, y sub 2. So x1, y1, and x2, y2. That just means they're generic points. They could be anything. But we'll refer to them as 2 different points. Those subscripts just mean that they're different points. So our formula for slope, we say m is equal to, it's the difference in the y's, so we write that as y sub 2 minus y sub 1 divided by x sub 2 minus x sub 1. Now notice those subscripts, they don't mean to square anything, they're not exponents, they're just to distinguish one point from another. The important thing with the slope formula is that you go in the same direction when you subtract on the top or the bottom. If I gave you 2 points, it doesn't matter which one you call x1, y1 and which one you call x2, y2. You're just going to subtract the y's and subtract the x's. Just make sure you do them in the same order or your sign is going to be messed up. Let me give you an example. If we had 2 points, and I'll just make up a couple numbers here. So suppose that my 2 points were 3, -1, which I put on the graph here, and 1, 5, which is here. If I wanted to try to come up with the the ratio of the rise to the run, I would subtract the y's and put that over the difference of the x's. So in my numerator, if I were using the formula, I've listed this point second and this point first. It doesn't really matter though. My formula would say to do the difference in the y's, which would be y2, my 5, minus my y1. Now we've got to be careful with the signs here. y1 is -1, so I need to be careful when I'm doing that subtraction. If you make mistakes with slopes, it's usually in this. It's usually in the signs. I put that over the difference of the x's. Now I need to start with, because I started with the 5, I need to start in the denominator with that 1. It does make a difference for me. So I would do 1 minus 3. And then I just clean that up. My slope would be 5 minus -1 is 6. 1 minus 3 is -2. And if I simplify that, I get a slope of -3. I said the slope should be written as a fraction, or we often write it as a fraction. Remember, a whole number is a fraction over 1. So if I'm looking at the slope here, I would say I'm going down 3 and over 1, down 3 and over 1. The ratio between any 2 points on that line is down 6 and over 2 or down 3 and over 1. All right, important things to keep in mind. Any line that increases from left to right, like this, has a positive slope. So I'm going to write m is greater than 0. Any line that decreases left to right, like that last example, has a negative slope. M is less than 0. If we can keep that in mind, most of this stays pretty easy. It's one place you're going to make a mistake. Remember to keep in mind that sign of the slope, positive or negative. In that last example I just gave, the slope was -3, and we notice that line is going downhill left to right. Horizontal line, a line like this, if we use our slope formula, so let's say we have a point here and a point here, we notice that, like if this was 3, 2 and this was 5, 2, our slope formula would say the difference in the y's, 2 minus 2, over the difference in the x's, 5 minus 3. My numerator here turns out to be 0, and 0 divided by anything is 0. So a horizontal line, we say, has a slope of 0. Now a vertical line is different. Vertical line, let's see, we said positive slopes go like this, negative slopes go like this. Well, what if those positive slopes got bigger and bigger and bigger? It started to get almost vertical, or a negative slope almost vertical. We get to the point where the positive slope and the negative slope are almost the same thing, right? If we think about them getting more and more and more and more vertical until they're almost the same thing. They can't be the same thing. They can't positive and negative be the same thing at the same time. What we actually say for vertical lines is that the slope is undefined. Sometimes we use the phrase no slope for vertical lines. Okay, so lines will either have a slope that's positive or negative or 0, but if it's vertical, it's undefined. And remember, if it's a vertical line, it's not actually a function, right? It wouldn't pass the vertical line test. All right, that's our page of notes on slope. We've got 2 more pages to get through, and then we'll pause.